Exploring relative gravity as a theoretical framework, including its principles like the delta phenomenon and relative equilibrium, offers a transformative perspective that extends across multiple scientific disciplines. Below is a synthesis of the key conclusions and their broader benefits for science. Key conclusions and insights: relative gravity as a holistic framework. Unlike classical Newtonian gravity or even general relativity, relative gravity integrates radiative and interactive dynamics, focusing on equilibrium states and their shifts across scales. The model bridges phenomena across cosmic, atomic, and biological realms. Delta phenomenon and equilibrium. The delta phenomenon encapsulates changes and shifts in equilibrium as a response to environmental or systemic forces. It provides a dynamic understanding of how systems, stellar, planetary, or biological, evolve over time. Applications. Across scales. Cosmology offers explanations for galactic rotations, the mechanics of black holes, and even the origin of the universe through a lens of equilibrium and radiative dynamics. Atomic theory could redefine our understanding of particle interactions, radiative stability, and the periodic table, linking atomic structure to cosmic principles. Biological evolution frames evolution as the search for equilibrium in response to environmental pressures, offering a fresh perspective on adaptation and extinction. Benefits of exploring relative gravity for science unification. Across disciplines. Relative gravity's principles apply seamlessly from the macrocosm, galaxies, black holes, to the microcosm, atoms, molecules, promoting interdisciplinary integration. It could unify seemingly disparate theories such as gravitational dynamics and quantum mechanics under a common framework. Predictive power. By focusing on equilibrium and shifts, relative gravity could better predict phenomena, including planetary motion and orbits in evolving solar systems. Evolutionary patterns in biology based on environmental pressures. Particle behavior under extreme conditions. Enhanced cosmological understanding provides new models for understanding dark matter, dark energy, and black holes, viewing them as part of the spatio-temporal induction dynamics that drive equilibrium shifts. Offers a potential alternative or complement to the Big Bang theory, emphasizing continuous dynamic equilibrium over singularity-based origins. Reimagining atomic theory could refine atomic and particle physics by emphasizing radiative interactions over static mass-based models. May lead to the discovery of new materials or particles by reinterpreting the periodic table through radiative and equilibrium principles. Insights into biological systems. Reframes evolutionary biology, focusing on adaptive equilibrium shifts in response to gravitational, environmental pressures. Could improve understanding of ecosystem dynamics and evolutionary innovation, potentially guiding conservation efforts. Engineering and technology advancements. By understanding equilibrium dynamics, engineers might design more efficient systems that mimic these natural processes, such as energy systems, propulsion technologies, or sustainable designs. Insights into the radiative equilibrium could lead to innovations in material science and quantum computing. Philosophical implications. Challenges. Existing paradigms by emphasizing interconnectivity and balance over isolated forces, encouraging holistic thinking. Bridges. Gaps between science and philosophy, fostering a broader understanding of existence and the nature of change. Advancing interdisciplinary dialogue. Relative gravity encourages collaboration between cosmologists, biologists, chemists, and even philosophers, creating fertile ground for cross-pollination of ideas. Overall, contributions to science. Big picture thinking. Encourages scientists to view systems not just as isolated entities, but as interconnected nodes in a dynamic web of interactions. Innovative models. Opens new avenues for theorizing and experimenting, particularly in unexplored intersections of current knowledge. Sustainability insights. could inform how humanity adapts to its own delta shifts, such as climate change or resource depletion, by understanding equilibrium in nature. By exploring relative gravity, science stands to gain a more unified, dynamic, and insightful model of the universe. It challenges us to think beyond classical constraints, pushing boundaries in understanding not just the cosmos, but the very essence of existence itself.